These are the notes for specific heat. If you are following along in your packet, this is on page 17. So just as a reminder, we'll go over heat, thermal energy, and temperature definitions. So just remember they are not all the same thing. Thermal energy is another word for the movement of particles. It's the total energy in an object. Heat is the transfer of thermal energy between two objects, kind of like work was the transfer of energy. Heat is just the name for thermal energy being transferred. And temperature is the average energy of the particles in an object. So remember, thermal energy is the total amount of energy based on the movement of particles. Heat is just the transfer of thermal energy, and temperature is the average energy, again, based on the movement of particles. So if we have two objects of the same temperature but different mass, they'll have different amounts of thermal energy. Remember that the more massive object has more particles, and therefore it will have more thermal energy just because it has more particles that contribute to its total energy. If we look at our new definition for today, it is specific heat, or that's our new term. So specific heat is the amount of heat required to increase the temperature of 1 kilogram of a substance by 1 degree Celsius, or Kelvin. Some materials, like metal, have a low specific heat, and therefore they increase temperature easily. If you think back to the simulation we did last week, the olive oil had a very low specific heat, and the water had a very high specific heat. So some materials, like water, have a high specific heat, and that means it takes a lot of heat to increase their temperature. Now we get into our equation for specific heat. Specific heat is in this equation, so it's heat equals mass times specific heat times the change in temperature. So if we want to know how much heat is transferred in an object, we just use this equation. It gets the variables Q equals mc delta T. So if we look at this, Q, remember, is heat, m is still mass, C is a new variable that is for specific heat, and then delta T, remember this delta just means change. We saw it in displacement, so like delta X was change in position or change in X. Here delta T just means change in temperature. So that delta, that triangle, just means change in, and then T for temperature. The units for these things, heat is in joules, mass needs to be in kilograms, specific heat, it gets these weird looking units, joules per kilogram degree Celsius. So just take a look at this, because anytime you see it in a problem, you know it means specific heat right away, because this is very different from anything else we've seen so far. And then lastly, change in temperature, that's just going to be degrees Celsius. So here's how we use that formula. Let's say we have a piece of glass, and the specific heat of glass is 753 joules per kilogram degree Celsius. If the temperature of the glass sample increases by 10 degrees Celsius when 2,450 joules of heat are applied, what is the mass of the sample? So we are going to use the equation to find the mass of the sample here. So our equation, once again, Q equals mc delta T. And now we need to identify what's Q, what's C, what's delta T, because remember, we're looking for mass, so that is going to stay our variable. So the trick is to look at units. So if we look here, 2,450 joules, just joules, that's heat. So that's going to be Q. Just degrees Celsius, that's going to be T, or delta T. And then the 753 joules per kilogram degree Celsius, remember these weird long units here, that's going to be specific heat, so that goes in for C. So if we substitute all that in, that's what we get. And then it's just an algebra problem from here. So take 753 times 10, that gets us 7,530. And then we just divide 2,450 by 7,530 to get mass. And then we find out the mass is 0.33 kilograms. Sometimes when we do these problems, we'll need to determine the initial or final temperature of an object. So in this case, we have a mug of hot chocolate that gives off 17,500 joules of energy to the air around it as it cools. So that's going to be important. If the hot chocolate has a mass of 0.2 kilograms and its final temperature is 32 degrees Celsius, we want to know what was its initial temperature. and then it tells us the specific heat of hot chocolate is just 3,930 joules per kilogram degree Celsius. So if we start to solve this one, same equation, but this time we need to be careful. So it says its final temperature is 32 degrees Celsius. It does not say its change in temperature is 32 degrees Celsius. So in that equation, we don't know change in temperature. So we do know heat, that's 17,500 joules here. We do know mass, that's the 0.2 kilograms. We do know the specific heat, but we don't know change in temperature. So this one's a little tricky because you do see a temperature, but just look closely, it says its final temperature is 32 degrees, whereas here we need the change in temperature. So then we can just solve this to get change in temperature. And we find out the hot chocolate is going to change its temperature by 22.3 degrees. So now what we need to do is determine, did it get 22.3 degrees colder or did it get 22.3 degrees warmer? In this case, our problem tells us that it cooled down. So we want to know the initial temperature. That means it must be higher than our final temperature, because if it's cooling down, the initial temperature had to be higher than 32 degrees. So what that means is we know the change in temperature. All we need to do is take our final temperature here, and to get the initial temperature, we know it's just 22.3 degrees warmer than that, because once again, this tells us how much it changed its temperature, and then we just read the problem to determine, did it heat up or cool down? So in this case, cooling down, that means it started above this number because its final temperature is 32, so it had to cool down to that number. So we just take our final temperature of 32 plus that change that we found in the first part using our Q equals mc delta T equation, add them together, and we find out that that's a mistake, that should say initial. The initial temperature is 54.3 degrees.